Hello, class. Okay, so we're going to talk about something called beats, or the beat frequency. So let's say we have two tuning forks. Let's say this is tuning fork 1, this is tuning fork 2, and we ring them both, we have them both going at the same time. And let's say the frequency of this one is 998 hertz, and the frequency of the other one is 1,000 hertz. Now, let's say you just do one at a time. So you have one tuning fork, say 998 hertz. You listen to it, then you stop it, then you take the other tuning fork, hit it. That one's 1,000 hertz. Can you tell the difference? Probably not. I guess it might depend on the person. Some people's ears are really good at detecting things like this. But again, these two are kind of producing the same sound. However, their frequencies are a little bit off. And what is the effect of that going to be? That leads to this very interesting phenomenon called the beat frequency. And so let's say we have an observer here. And remember our wave in general, it's a function of x and t. Alright, so our general wave, we can use a cosine to describe it. And then we have, it involves a frequency and the x location where the observer is. And so let's just, the observer is fixed in place. And so we can ignore this term and say each wave is going to look just like the first term. So we can say that y1 is going to be a times cosine of 2 pi f1t. Now the next term we just ignore. Because it's a constant, that's not going to affect anything. If we included it, it would just make the math more complicated, but wouldn't have any effect at the end. So we can just set x equals 0. How about that? Okay, and then y2 is going to be a cosine 2 pi f2 times t. And so these are the amplitude of these pressure waves at the location of the observer as a function of time. And so because there's two sources of sound, the resulting wave is simply going to be the sum. We can in general say that y equals y1 plus y2. So we want to add these two waves. Okay, now this is one of those cases where we're going to have to use a formula from trigonometry, which is not a prerequisite for this class. So I'm going to write down this formula. Cosine of A times cosine of B. And I'm going to write this down. That's equal to I'm going to write it down somewhere else because I don't think I have room over here. Cosine of A times cosine of B So that's a formula from trigonometry. You might have never seen that before. If you have any doubt about this, remember A and B are just angles just make up a random angle. You don't want to pick special angles like 0 or 90 or 45. And again, this is certainly not a proof, but say A equals 12 degrees and B equals 48 degrees. You can just plug those in on both sides and you'll see those are equal to each other. This is definitely not proof, but it might convince you a little bit. I'm not going to try to prove this formula. That's not what we want to do here. And we want to relate that. We want to add these two waves, which in general is fairly complicated, but in this particular case, it's manageable if we use this formula. So what we're going to do is we're going to make some substitutions here. I want to change my notation a little bit because I'm using A here and A in this formula. Let's call this Y max. The amplitude, we'll call that Y max, just so we don't confuse the amplitude with the A in this formula. So what we're going to do is we're going to define, I'm trying to figure out where I can write this and still have room. I'll just write it here. Let's say that A minus B equals 2 pi f1, and A plus B equals 2 pi f2. So, and I did it this way because A minus B is obviously going to be less than A plus B if we're dealing with, positive numbers here, and f1 is less than f2. So let's just do that. Now if we add these two equations, if we just add the left sides, we're going to have 2a. The b's cancel out. So 2a is going to be 2 pi times f1 plus f2. And if we take the second equation and subtract the first, here we're going to have a minus a, b minus negative b gives us 2b, and that's going to give us 2 pi times f2 minus f1. And so at this point, I'm going to tell you, what we're doing is a fairly complicated thing. It involves this trig identity you may have never seen before, adding cosines. But I promise you the end result is going to be about as easy as anything you can imagine. So just bear with this. I want to show how we can actually get to this ending result. Okay, so what we have here, I want to rewrite this. Cosine A minus B, A minus B, that's 2 pi f1. Sorry, I'm going to put a t at the end of each of these. And it still works if you do that. If we add them, we get 2a. The 2 pi and the t factor out. So have f1 plus f2. Same with taking this equation and subtracting that one. Okay. And then we have plus cosine of a plus b. That's 2 pi f2 times t. Divided by 2 equals this. Equals cosine, I'll just write it cosine A, cosine B, because that's all I have room for. Okay. Sorry. Yeah, on the left side, we had cosine A minus B, which is 2 pi f1t, and then cosine A plus B, which is 2 pi f2t, and then we move the 2 over here, so we have 2 cosine A, cosine B. Now, let's multiply both sides by y max. So here we're going to have y max times 2 pi f1t, or cosine 2 pi f1t. This is just going to be y1, and the second term is just going to be y2. So if we multiply both sides of the equation by our amplitude, on the left side we have y1 plus y2, and then we're going to have 2 y max times cosine A, which I'm going to write like this. So 2a is equal to this, so we're going to divide it by 2, but I'm going to do this in a particular way. Now, unfortunately, I'm out of room, so I'm going to erase it, try to cram it in here. On the left side, we have y1 plus y2. That's 2 y max times cosine f1 plus f2 over 2. So yeah, a is 2 pi f1 plus f2. I put the divided by 2 on that term times t. Now, we could cancel out these 2's, but we don't want to. And then we have cosine b. We're going to do the same thing. We're going to divide by 2, but put it under there. I barely managed to fit it on here. But this is the result that we wanted. Okay, so let's look at, I think I'm going to erase this. We used it, we don't need it anymore, so let's get rid of it. And let's just put a big circle around the final result. Actually, I can do one more thing. Remember, y is what the amplitude the observer is going to see. Like this. So you notice f1 plus f2 over 2, that's the average value of those two frequencies. And then we're going to multiply that. We're going to look at it as two things. This thing times cosine 2 pi. I'll just write it as it is. Okay, so this is the result that we've been looking for. Okay, now let's ignore this for a moment. Let's see if I can block this out. There we go. Okay, I think it's good here. Okay, so if we ignore that last factor, let's look at what we have here. In this example, f1 is 998 hertz, f2 is 1,000. So in this case, the average frequency is 999 hertz. And again, difference between 998 hertz and 999, no big deal. And so what we're looking at here, we have these two sources, and this result is telling us that we have the average frequency, but double the amplitude. This is kind of an expected result. You have two sources with the same amplitude, y max. You bring them together, and you get the average frequency and double the amplitude. Very logical, expected. But what about this other term? Let's look at f2 minus f1 over 2. F2 minus F1 is 2 hertz. Divided by 2, this is 1 hertz. And so 1 hertz, that's 1 cycle per second. So we have a cosine of this, let me write it here. Let's look at cosine of 2 pi times 1 hertz, which is 1 cycle per second, times t. So t is measured in seconds, and we have a second, hertz a cycle per second. So basically we just have this. So if we plot this over a time interval of 1 second, we go through a full cycle. So let's say t, here's 1 second. So we go like this. More like this. Here. That's what we're plotting on the y-axis. So over 1 cycle, over the this here is 1 hertz. And like F2 minus F1 over 2 is 1 hertz. So over a period of 1 second, we're going to take this thing, which is oscillating very quickly. Here we've got about 1,000, we have 999 cycles per second. And again, if you listen to a sound with a frequency of 999 hertz, you're not going to be listening and saying, yeah, it's going up and down really quickly. It's going way too fast for you to hear it moving up and down like that. It's just a particular sound. And so you're just going to hear like this buzzing sound that's this pure tone at 999 hertz. However, we're multiplying by this, which goes to 0 twice. Because remember, we're multiplying here. So at this particular time, yeah, like this would be, in this example, this is 0.25 seconds. The sound is going to drop to 0. So if it wasn't for this term, you just hear that average frequency from your two sources. But here at t equals 0, it's like you're hearing maximum amplitude. But then a quarter of a second later, the sound is going to drop to 0. And now, again, sounds are negative, never negative. It turns out the amplitude, the intensity of the sound is related to the amplitude squared. So we're going to get maximum amplitude here as well. This will be, so like right here at 0, say it's very loud. And then after 1 second, it's loud. And after half of a second, it's loud again. So it doesn't matter that the amplitude is negative. That's still going to produce the loud sound, because we're going to square these values so the negative doesn't matter. So after half of a second, we're going to get, so it's going to go through like this whole cycle in just half of a second. And so the sound goes from like loud to 0, back to loud, and then 0 and back to loud. It goes through 2 cycles in every second. And so basically we ignore this 2 here because we go through 2 cycles, like 2 periods of like, we go from, starting from say, loud, we go to 0, loud, 0, and back to loud. Like hit each one twice during that cycle. So what we're going to do is we're going to define what we call the beat frequency. That would be F2 minus F1. And that kind of modulates how quickly the sound rises and falls. Like if you listen to it, 1 second, that's something you can definitely notice. You'll notice the sound go from maximum amplitude down to 0. You'll hear it rising and falling. And the closer these are, this is the frequency, F2 minus F1, that's the frequency, called the beat frequency. And remember, the period is 1 over the frequency. So if these two frequencies are close together, the beat frequency would be very small, which means the period would be very large. So if these tuning forks were both like, say, 1,000 and 1,000.1, if you hit them both together, you'd have to wait for a long time to hear that sound drop and then rise again. But the more off these are, the more quickly, the bigger the beat frequency, the smaller the period. So it'll take a shorter time for the sound to go through its cycle, this up and down cycle. And so that's beat frequency. And these are important. They have some applications. It's kind of interesting in its own right. But they have applications as well. One is tuning an instrument. They have tuning forks that, they oscillate at a known frequency. And so if you, say you have a tuning fork at, say, 512 hertz. I'm going to erase all this. Really what we need is this part in the box. Oh yeah, so I mentioned earlier, showing how the beat frequency works, that was pretty complicated. But here, if I ask you what the beat frequency is, subtract the 2. Actually, I think we have an absolute value on there because we want it to always be positive. So just take the big one, subtract the smaller one, there's your beat frequency. So again, the end result is nice and simple. Let's say we have a stringed instrument like a guitar, and so we've got all these different strings, they have different densities, so remember the wave depends on the tension, and also on the density. So these strings have different densities. And again, like you hold down a string, let's say you put your finger here and pluck the string, it's going to oscillate with a certain frequency. And say that you want to produce a note that's, say, 512 hertz. But say it doesn't sound quite right. Say your guitar is out of tune. How do you tune it? Well, what you do is you get a tuning fork. Like, say you're trying to produce 512 hertz, but say it's significantly off, like 520 hertz. And say you have a tuning fork, which is at 512 hertz, and what you do is you pluck the string and hit the tuning fork and just listen to the combined sound, and here the beat frequency would be 8 hertz. It would be going up and down, like a frequency of 8 hertz. And so the period, that'd be pretty quickly. The period would be 1/8 of a second. So it'd be going like through a full cycle 8 times every second, like the sound rising and falling. That'd be a pretty high beat frequency. And so remember, the speed of a wave depends on the tension in the string. So you've got those knobs on the guitar. You can tighten it or loosen it to adjust the tension and change the frequency. And say you adjust it and get the frequency here down to 513 hertz. Now the beat frequency is only 1 hertz. So you can definitely tell you've made an improvement. When you listen to the sound, it goes, much more slowly from loud to soft, loud to soft. In this case, they're not going to be the same amplitude, so they're not going to cancel each other out perfectly, but you can still hear that sound rising and falling. And the closer you get, the longer it's going to take for that sound to go up and down. And so just like, eventually you'll get to the point where you don't even notice anymore, and then you can say your instrument is in tune. So that's the beat frequency. Again, one of the more difficult things mathematically that we had to do, but the end result, just subtract. Very simple. But you should understand the concept behind it. And again, this is when two sounds are very close together in frequency, and then like the overall sound, you got to get that average frequency, but it rises and falls with this beat frequency, which is just the simple difference between the two. Okay, so that'll be it for this. And then we have one more topic in this class, and we're done.